Hello everyone. I think let's start. Set up, right? Can you guys can hear me, right? I'm assuming that you guys can hear me. Right. Okay. So let me just quickly share my screen and today is essentially we will finish our lessons today. Let me just share it first. And so yeah, let's start on the conversation. So any questions on the yesterday's session? Are we on the same page with autoencoders? We discussed quite a bit on autoencoders, right? What it does. This is actually this problem statement. If you see, right, if you see the specific history of autoencoders, it's there for some time. In 1980s, if I'm not wrong. But this new class of algorithm is using neural net restarted, I think, from 2005, if I'm not wrong. Again, on the insistence on a novel paper by Mr. Hinton, okay, Geoffrey Hinton, father of neural network, right? He is the one who has actually re-architected the backward propagation. He was one of them, right? Um, So I think it's a pretty interesting algorithm and lot of usage of autoencoder. This is about we will just do a theory of it, but if you actually I'm not sure whether if you do there's an advanced course on the computer vision, okay, which is almost equal length of this course, but only on vision. Um, I'm not sure actually, but I think they'll definitely be having a autoencoder or variable autoencoder, some sort of autoencoder detail there. But nevertheless, I think this kind of an architecture sort of makes sense to us, right? Given an image, if you encode, the idea of encode and decode is existing in everywhere, right? Your video player is actually an encoder decoder idea, isn't it? When any video streamer, YouTube or anyone, sends the stream over the wire, it encodes it, compresses it, and the player which is running on your mobile or your laptop decodes it back, right? That's the same thing with any radio frequencies, isn't it? Or with any speech system, or even music itself, right? So this encoder decoder kind of a concept is there from long time. Encoder, what it does when it goes to when you actually encode, you get a compressed representation, but when you decode, at least in autoencoder, you will have some sort of loss, right? And that whether the loss is acceptable or not is a question that we can answer, and maybe there are other kind of mechanisms and tools and techniques where you can reduce that loss. But one thing is clear that if you reduce an image, encoder will have some sort of CNN. In this case, it is image, right? It will reduce the image. At least the bits will be reduced, right? The dimensions might not, but the information in the image will be reduced to a compressed representation, and then you can bring it back. That yeah, JPEG, yes, absolutely. JPEG is also does that, right? JPEG is if you see the JPEG's algorithm, right? It is amazingly complex, and it's one of the most revolutionary idea of lossless compression. What in the algorithm is really awesome, and it's open. You can actually look at that. Yeah, lossly. Yes, exactly. But so this is here. This is also a lossly compression, right? Um, but JPEG's thing is like really awesome. If you see that the work that has happened in image or the representation of image has been extremely huge, right? But in this case, so in case of JPEG and all, what happens is that you have uh, okay, yeah, probably yes, he's famous for test data, yeah. So in this case, what happens? We will use neural network, right? So the JPEG creations or any kinds of the image creations is essentially nothing but you will have some sort of format which outputs it, right? In this case, what are we trying to do? We are trying to learn the format, right? And so that is something that, and why are we learning it? We can learn it, we will learn it because it has a lot of usages. Of course, autoencoders can reduce our dimensionality. You can learn this compressed representation, right? And we have seen that one of the intuitive way of using it is that if you do have a compressed representation which can mean a world of good, like in case of language, right? You can represent something of an encoder, embedder, which might represent the world's language. Sorry, the world's knowledge. You can also do denoising, right? There was a question on image denoising. Are we clear on that now? I think yesterday there was a question. What is denoising? You have an image which is a very old image, right? Well, I don't know how many of you remember, but earlier we used to have those print images, extremely old images, right? And if you take a print and there's a need to actually clear the image out, so you can denoise it. That's a image with lots of noise, so you can actually do a denoising. Image denoising algorithms can use autoencoders, and it's just not one algorithm. You can learn based on the image or the data set how to denoise any kind of denoise. Like suppose you have that's what I'm saying, right? If you have a very old okay, if you have a very old let me just try to search something noisy images, right? So I can just share it. Let me just see this. This is right. So you can see my screen, my Google screen. So this is a noisy image, right? This is nothing but a noisy image, right? So we know Lena, right? We have looked at Lena. So this is a noisy image. Like yeah, it's unwanted thing, right? So the image is noisy for whatever reason, whether the image quality is bad or not. So but you can clear this if you send it via an autoencoder, right? Reduces grainy image. Yes, yeah. Well, there can be other things also. In fact, let's go here. And I was like, so Keras has a very, so see this. So this is a MNIST noisy image on 2103. In fact, in real world, you will not have very clear image, right? Someone will take a picture and that might not be very clear given the conditions, right? Any kind of conditions, right? Grainy image, the image is not clear, it was cloudy and so on and so forth, right? But from here, you can have a clean image. We still have been working with very clean images. Do you think when someone actually traffic cam images, yeah? Do you think this is MNIST was handwritten digits, right? Did someone really write like this and someone took a picture? I don't think so, right? In fact, that will have been made clear in Jan LeCun's page on MNIST, right? But I don't think so, right? So there must be some sort of image processing that was done, isn't it? To clear stuff up. So this is an example of a noisy image, and if your output of so this is an example of a noisy image. Your output can be a clean image, right? So that is one thing that we can um, you know understand. So similarly, this is an image of the same Lena image with grains. If you pass it via auto encoding systems, it's possible that you will have a very clear image output. Okay, and the mesh system will learn. The network will try to learn what sort of noise is it rather than hard coding things, right? This is non-linear in nature, right? We can use PCA, but PCA's problem was PCA had linearity, right? Fundamentally, right? PCA is a linear algorithm. It might not be great on non-linear data. However, auto-encoding or encoding or decoding for that matter is thing. Okay, anomaly detection. We spoke about anomaly detection. Lots of anomalies everywhere. Okay, if you have extremely large amount of volume, it can detect, and most importantly, this feature representation or feature learning itself. You can learn a feature, which is actually of huge importance. Your encoder and decoder. How does it do it? It has four components, right? You have an encoder, then you have the bottleneck, which is nothing but it's called as bottleneck because you stop the encoder there after the encoding is done. Okay, that's your feature representation. Then you decode it back, right? How will you decode it back? Any idea? Any guess? How can you decode things back? So how do you do it in machine learning? Think about it. If you have less data and you have to project it at a project and you have to increase the data, what do? What is that process that called? When you have very less data, when you have data imbalance, think about it, right? What do we do? If you have less data and then you have to find out more data from somewhere, I don't know where it is, from wherever you have to find out and put it. We have to do upsampling, exactly. So that's exactly what we do, right? You'll try to do some sort of upsampling because exactly. So some sort of upsampling has to be done in a way that it's representational. So you will do. Yeah, but the objective is not what is an objective? Overfit is fine, but what is my objective? My objective is to represent the my feature representation, right? So if you actually remember, right? So how does it look like? So this is if you have to formulate an autoencoder, right? There is no autoencoder is an unsupervised learning technique, right? You do not have any while. So you pass all your images via an encoder, which gives you a compressed function, and then you decode it back. Okay, sorry, yeah, you decode it back, right? Via this method of upsampling or whatever method you choose, right? But this is also a neural network, and output will be basically some version of X. Your objective is that to match how different these two versions are, right? And that will be your objective, right? So what that objective is called as reconstruction loss here. What is the loss of your reconstruction, right? And if it is too big, then you already know that, okay, my network is not good. The backpropagation will kick in and just change the weights to ensure that your x bar or x hat minus x is minimum. But the thing is that you already lost something. From there, how do you get it back? You need to fill something, right? You cannot cook up some numbers. So that's generally what you will have to do, right? Upsampling, some form of upsampling. Of course, it's not going to be, it's not going to be, there are many types of algorithms to do it properly, but the idea is that, right? Isn't it? If you have to, and if you have to formulate by functions, you essentially have two functions, right? And of course, the loss is also a function. You will have a separate network which focuses only on the encoder. Its output goes into a decoder, right? And and then we'll have a distance computation between x bar, between uh, sorry, between x bar and this is x bar minus x, isn't it? So if we do a formulation, I mean, in the spirit of putting a formula to everything, and why do we put a formula? It just becomes easier for us to represent, right? Of one function can be representational for the whole network. We don't have to worry about it, right? So if f of x, which is nothing but our encoder, right, is some sort of sigmoid function. S is nothing but some sort of activation function, right? each of my x's goes via some sort of weighted weighted multiplication. This is a linearity, right? And then you add it via bias, right? So this you can name this as a function. Then g of z, basically g of f of x, will be another function. So the whole of network can be represented something like this. My x bar, or in this case, so my y is nothing but x bar, will be g of f of x. Why? It just now if you can expand this function again and again and again, it just gets easier for you to put things. It's basically one function, and functions are by default differentiable. You can do some sort of backward propagation. You can find out that if you have to change d of x bar against of d of w's, and then change the weights and biases accordingly, isn't it? And that's what we have to do. And of course, there are other sort of techniques also, but at its root level, this is what a neural network will try to do, right? It will try to it will downsize me and then upsize me and then try to match my version of upsizing with my original version and see how much big difference is it. If there is a huge difference, it will continue to learn. If there is a small difference, its objective is to go down to a smaller difference, and that's the feature representation is what is important here. So this is a very important mechanism to auto learn things or to create feature representations, right? If you have to generate a feature representation, if you have to, how will you do it? Or in a very unsupervised learning way. This is a very typical way of doing it. Okay, run a network via data, get some feature representation, and then scale it up. Check the difference amongst themselves, right? You do not need a y. Your input itself becomes a y. And you will see this idea coming again and again in many places of of creating this feature representation matrix, right? So this should be pretty easy for us now. Okay, g of f of x, and you can complicate it. You can continue to expand it as much as possible, because f of x is not one function; it's a bunch of functions, right? But at a high formulation, at a high level, this is what it looks like, isn't it? So h is nothing but an approximation of an identity function. What's an identity function? Not reconstructed. This is not reconstructed. This is the part of the decoder, right? W bar and y bar, or W prime or Y prime, whatever you call, are the weights for the decoder. So this is my decoder network, and this is my encoder network. F of x is the network encoder function. G of z is my decoder function. Okay. So both of them will have their own individual weights and biases, right? So just to indicate which weight is what is that you have to use, right? So just again enforcing the idea that this sort of equation or formulation in a neural network is easy, and if you actually look at it, you just have to get a little used to it. Once you get used to it, you will be able to read a lot more of these papers that you can think of. Okay, and I think that it is good for us to know. So what is an identity function? H is nothing but H is the final function. What is an identity function? So it's basically the same function, right? If you multiply an identity matrix with itself, you will become that, right? So you're trying to find what is an identity. Do you remember what is an identity matrix? In matrix multiplication, what is an identity matrix? It is just like multiply by 1, right? 1 is an identity scalar, right? If you multiply anything with 1, you're gonna get that. But if in a matrix multiplication, you need to have a identity matrix is all the diagonals are 1, right? Remember, that's how you're going to reproduce the same matrix, right? Similarly, you're also basically trying to generate an identity function which will copy the x to the same x as much as possible. So you're trying to approximate or optimize the loss on that particular identity function. So why these notations or these sentences or these jargons, if I may, are important for you? Because whenever you start reading blogs, right, various people might formulate is that h of x and g of z are No, the h of x and g of z are not same, right? H of x is the final function. Yeah, you can say that. Yes, yeah. H of x is and g of z are basically both are same, but what we do is, yeah, exactly. But the thing is that we always, what are we doing? We always actually, it's in our interest to represent everything in my x, what is in the inversion of my x, in my input and weights. If I do this, my problem is solved because I then have only one variable to tackle, which is x. X is anyway x is something that you can't change because x for us is input, right? What can you change? You can't change, so you only change w and b. So why do we write like this? It's a good question actually. Why do we always change everything in the form of x? Because then you can clearly build a relationship between x bar and x. If you add more terms, then you have to worry about those other terms. What are those terms? What are those terms? You could have easily written x bar equals to gz, right? You could have written that, but then what is z? So then in our mind, x is an input, x bar is the output. This is the relationship which is, so you will always see that all the functions, even in our functions also, if you remember, we will always represent loss in the terms of x, and x is input and weights and biases. So that x is something that we cannot touch because it's just data from data set. All we change is w and b. It is just more interpretable, and then we have to deal with less terms, less unknown terms, or less terms for that matter. Okay, one way to imagine. Okay, how do we train an autoencoder? That's you train the model from an optimization standpoint. We will definitely use some sort of gradient descent, right? If from an optimization standpoint, however, from loss standpoint, what do you think that we will use? Okay, let's go there since we have already revealed the question answer. From a loss standpoint, it is saying here that we will use a squared loss function. Why do you think we will use a squared loss function? Why can't we use a binary cross entropy or categorical cross entropy or something else? I mean, you can use, but it will not be great. No one is stopping you to use, but why can't we use? Why will we, can you just think why will we use some sort of loss function which looks like this? This is a typical, what sort of loss function is this? This is a regressor kind of a loss function, right? This is a loss function of a regressor, right? It's not a classification loss function. So you're trying to, it makes sense, right? You're trying to find the distance between your input and output. And if your distance is really small, then voila, you have done it, right? Then you probably almost represented whatever my input is. So that is the reason, this is exactly that, right? So distance, and why do we do square? Just to negate your, first of all, to negate the negative, and then if you do a square, then what is the other thing that happens if you do a square? So you can say that, okay, I understood that this is a loss function, but you could have used MAE kind of a thing, right? Average, so it could be an x bar minus x only. Then why do we do square? Apart from the negative part, one thing is very clear, that we need to remove that negative loss. No. So yeah, always makes positive is fine, but outlier of what? What is outlier? This is a neural network. Outlier is already handled in the network, right? Why do we do square for a loss function like this? Do you remember? If you don't do square, what will be the loss function's shape? Will it be parabola? It will not be parabola, right? A square will make it parabolic. If you have parabolic, then you can apply this gradient descent. Slopes will come and all, right? That is one of the reasons you can actually do square. If you square it up, then it will have that shape, U shape, a concave or convex type of shape. In this case, we are interested in concave, right? The U one. And then we want it to go down to loss 0. So that is also one of the important, of course, to make it negative, right? But you can also take the magnitude of, you can say that whatever is negative, positive, I will only take the magnitude, right? Not take the positive, but the more important thing is that if you do a square, No, no. If you do a square, what happens? Do you remember? If you do a square, if you don't do a square, if you will not get, sorry, if you don't do a square, you will not get things like this. It will not be like this, right? And if it is not like this, where is the question of slope and all will come? It's going to be very difficult for you to draw and run that gradient descent function, right? And if you have this kind of things, then only you will have a easier way to find out the gradient descent, right? It's an important understanding. Remember that. Okay. So if input is interpreted as bit vectors, the cross entropy can be used as a loss function. You can see this, right? If your input is 2 is the so this is the symbol of this thing, magnitude is false, right? All you're going to take is magnitude, right? And this square it up, it doesn't matter. Right? So that's a signal symbol of minus 2 of this will be 2, 2 of this also will be 2. That's all it is. It is absolute. You can say that absolute, right? Okay. So what are the types of autoencoders that we have? We have, we have many types of autoencoder, but I think for the purpose of this discussion, what we will discuss is probably we'll go through under complete autoencoder and over complete autoencoder. Okay. In its name, we have some sort of meaning already hidden. Okay. The under complete autoencoders are, those kind of encoders where your hidden layer, the feature representation, okay, is actually smaller in size. Okay. What happens if you have smaller in size? This is where, so your x is what, 6 neurons or 6 inputs. You have x, so from the down, right? Let's go from the down, right? So my x is 6. If my x has 6 pixel, I must, or my x bar also should be 6 pixel, isn't it? It must be. There is no other way, right? So when I pass it via a input layer, a hidden layer like this, which is lesser than the 6 examples or neurons that I have, which essentially means that I am compressing it, right? I am really compressing it. It compresses the output, okay? Only for the training distribution. You are compressing only for, this is x is nothing but training distribution, right? Right? So hidden nodes is, in this case, it's good for training distribution. Good. You have learned really good features for training distribution. But this kind of thing might be problematic for other types of features, right? If you have. And when you actually explode, you need to actually do something, right? Some sort of upsampling technique. It's definitely going to be some sort of upsampling technique. You will fill with pad 0, 1, -1, some sort of, right? How will you fill those 3 pixels? You have these 3. You need to actually get from somewhere, from thin air, 3 more pixels, right? Whatever is it, you have to add 3 more pixels. And then you have to compute, right? So that idea of that, how can you add? You can simply add 0, 0, 2 zeros on the both side of it, right? So that your feature representation is not corrupted, because this might mean something. However, when you actually project it out, it might be a little less perfect what we have actually done, right? So but this means that your input, your hidden layer is already compressed, right? And it's already compressed, and this is generally a way to, you will always see that you will have a large features, and that PCA is all about dimensional reduction. We did a dimensional reduction here. You can consider something like that, right? It's like a PCA kind of a thing that you did. You reduce the dimension to fx on this output, and you can actually take this output and use it in your embedding matrix if you are using language, or using as you can use as a transfer learning approach for your other vision kind of a architecture. Okay. The other one is just the opposite, which is nothing over complete, right? Your hidden layer has many more neurons than what it should be. So what it should be, as in what it is there in the input. Okay. And there's there is some sort of convolution, there is some sort of lossiness or compression, but it's spread out. Okay. The compression you can say is not much there. Okay, but in any ways, right, if you actually run a convolution layer, right, there will be some sort of compression. Only thing is that you are spreading out that. Okay, so that is what it's been doing. It's actually adding a dimension is good for training a linear classifier, isn't it? Think about it, right? What sort of thing this is what we're doing? We are adding more dimensions, right? So that is, we have added more dimensions, isn't it? Instead of reductionality of dimensions, we've added addition of dimensions, okay? Um, and but it can also cope with, so this is important actually, very rightly so, is that a higher dimension code might helps the model to form a more complex distribution. If you have a very complicated X, right? So it might be easier for you to actually expand your features, right? And then, again, compress it back to my X bar, right? See, code point of view, don't worry. Code is just two lines essentially. Like at least the one that we will go through it is basically, you can already imagine what the code will be, right? This will be one dense layer. This is one dense layer, and this another will be one dense layer. At its lowest level is with, you can complete this with two layers itself, right? And then wrap it up with some sort of a loss function, right? Which can compute a distance, right? And that's what you can do, right? When we look into that is what it is, right? But idea is important. So anomaly detection is very straightforward. It's basically an identification of an event which is generally you have not observed. There are clusters of events which you can identify, but suddenly there is an outlier that has happened. And how do and in if you are in the business of anomaly detection, outliers are not good. They indicate something which is not the normal trend, right? And they should raise a suspicion. Suddenly you have billions of requests coming from 3 or 4 IP addresses. Not good, right? And you have to deal with that, right? We will build this thing. Let's finish it off. So I think this is done. Oh, okay, that's about it. Okay. So this is what our autoencoder code is. What we'll do is like, let us go to. I don't think this. So you can, there's in Keras you have a lot of code examples. Okay, using so there's in time series anomaly detection also you can using autoencoder. There's like they're not that old, 2-3 years old. But I think you should actually start looking at it. Time series. So this is actually a real problem, right? Time series anomaly detection is heavily used in network. Network NMS system, network management systems. Okay, where you have, think of a company like Akamai, which is almost a gateway to all of the, like most of the internet traffic goes through them, right? If suddenly you see a part of the network has extremely large thing, right? It's also a time series data. Everything is time stamped, right? You need to, why you need to, can you guys understand? So maybe what Akamai has seen is that during COVID, their network has loaded has increased because a lot of people have started watching. They were at home and they were watching a lot of OTT platforms, right, at home. But that was anomaly at that time. But that is something bad. Just because there is an anomaly, that doesn't mean it will be bad, right? So those kind of things also are there that you have to worry about from a business standpoint. If you actually see this page in Keras, blog.keras, this is quite old, and this was actually documented by Francois Chollet. He is the inventor of Keras actually, works in Google, okay? Very famous researcher. So this is exactly the implementation of autoencoder, and you will see that so autoencoders are data specific. This is different. So it actually says that this MP3 is a compression algorithm, right? It compresses things, right? And but this is different. Why? And it also explains that why it is different. It also explains a little bit. Autoencoders are lossy, which means the decompressed output will be degraded compared to the original inputs, right? MP3 actually degrades it, right? And JPEG also is degradation, but there it is actually different than the zip. Zip is also degrades, right? Zip is also zips it, but when you unzip it, think about it, right? When you right click compress and then right click decompress, right? There is no loss on the decompressions, right? Right. Even the zip BZ2, BZ2 is generally good, right? And then there are other types of lossless compressions, but this is generally lossy. And autoencoders only objective is that you don't have to tell anything, give it the data, it will learn from the data, which is a good property to have, right? If we had this thing earlier, we didn't have to build different sort of algorithms for different types of files, right? I'm just saying. Okay, it means it's easy to train specialized instances of algorithm, and you can scale such things very easily. It doesn't require any new engineering effort, just some data. Okay, so that is what it is, right? Um, so he represents this very nicely actually. I will highly encourage you to go through it. And this is something that we will actually run now. I wanted to show you. This is something that we've discussed, right? This lossless loss is something that we have discussed, right? Yeah. So this is no, yeah. So this is the image denoising part, right? So this is an MNIST training example, which is with a lot of noise. Okay, and if you run it via an autoencoder, it goes to the feature representation. The features are all about 2104, not about the noise. The noise is removed from the features, and when you deconstruct it back, you have a much clearer picture. Okay, because a lot of links are there. So let's do one thing. I forgot to start my practice lab. Let's start my practice lab, and let's quickly build an autoencoder model. You will see that it's probably the simplest of the exercises that you have done. However, it's very complicated in from an understanding standpoint. It's very complicated. If you want to see the updated versions, just go to VAE. Okay, this is also so VAE is a variational autoencoder, much deeper than the one that we will train. Okay, and if you actually see, there's a lot of other types of so this is part of actually generative deep learning, right? So let's see whether we have this or not. Let me close all of this. Okay, we have I have only 6 hours of things left. I don't know. Okay. So lesson 8 is this, and if you actually see this, right? All right. So you see this, we have just Keras importing model, nothing outlandish right now. So this is my first encoder layer. Okay. Um, I probably will load MNIST somewhere. Yeah. So this is fashion MNIST. Have you heard of fashion MNIST? Okay. So this is a new data set. Okay. Good. Have you heard of fashion MNIST, folks? Import Keras SK. Fashion MNIST is one more data set like MNIST. Okay. It's if you actually see this, it looks like this fashion MNIST. Okay. MNIST like dataset for fashion product. So it looks like this. Okay. You have black and white gray images. Okay. For various types of shirt, pants, shoes, bags, and so on and so forth. And this is also a very nice image dataset, toy image datasets, but it is easy for you to. It's better than it's you have 10 classes. Here you have more classes, right? I forgot how many classes we have. Let's find out how many classes we have. So MNIST is too easy. Okay, MNIST is overused. People have got bored of it, right? So MNIST cannot represent modern computer vision tasks. Hence, and there is a Twitter thread from Francois Charlotte itself, right? Itself. So this is basically, you can see this is still 9. This is still 10 classes, but it is much more complicated, much more a little bit complicated than MNIST, normal MNIST. So this is called as fashion MNIST. Okay. So let's load that. So this is what is our encoder architecture. Let's look at it. It's very simple. We have our encoding dimension of 32. Okay. What is our shape? Do you remember what is our shape of an any MNIST? So this is the same shape. It's like it was, remember, to 28 by 28, right? So that will be around 784. If you stretch it out, it will be 784. That's our input image shape, right? And so you just do an encoding. This is the encoded layer, and this is the decoded layer. That's about it. So you encode from encoding dimension to 32, right? So you from your input 784 to 32 dimension, 32 to 784 dimension. Basically, this is your input layer, this is your encoding, this is your encoder, and this is your decoder. You are done. That's all it is. Right? And decoder goes via sigmoid. Why sigmoid? Can anyone think that why do we need sigmoid? In this case, we only want to know because there is only one class. You can use, as I said, right? You can use binary cross entropy. But can anyone tell me what is the difference between sigmoid and softmax? When should you use intuitively and when should you use softmax? Do we understand that idea? Maybe this is something for a discussion. Okay, let me add it. I think a lot of people get confused. Let me add it in our list of things to discuss. We'll discuss. Check if you are okay with it. Sigmoid versus what? Softmax, right? Which is for multi-class? Softmax is for multi-class. Okay, fine. But can you give me a little bit more detail? Okay, fine. So softmax is for multi-class, but you cannot stop me to add sigmoid, right? Suppose this is a multi-class. Suppose this is actually multi-class, right? So if I use MNIST, no, sigmoid doesn't give you sigmoid also gives you number between 0 and 1. Softmax also gives you number between 0 and 1. Both gives you number between 0 and 1. Okay, and it gives sum of 1. No, it doesn't give sum of 1. Softmax, if you see the whatever output of softmax is that if you add all the probabilities, all those numbers, they will be equal to sum of 1. So softmax is a true probability across all the outputs of that function. But in case of sigmoid, that is not true. Sigmoid will independently evaluate each of them. There is no link between them. The probability distribution is not on the all of the data sets, right? Softmax will give multiple probabilities for multiple output and sum of all probabilities is 1. That is correct. But sigmoid will independently evaluate each of them, right? So their sum will never be 1. So if you have a problem, so if your problem is multi-level classification, right? Suppose you have a problem of, your problem is to, sorry, let's go to this thing, first fashion MNIST. Suppose your problem is to detect, if you have a big picture, there's a shoe and a shirt, both are there. So this is a multi-level probability, right? So this is a multi-level class. Till now, what we are doing is that out of many possibilities, which one should I do? But there might be a problem statement that in a picture detect all those objects, right? So in those cases, what will you use? If you have to use a multi-class, multi-level problem, you have a multi-level class, right? So let me just write it down, okay? So this is a very common problem that we'll see, which is basically what I'm saying is that what is multi-class versus multi-level, okay? So this is something that we can discuss. This is a very common problem that you will see, okay? There are problem statements which will require you to predict multiple things at the same prediction, and then there are problem statements which will require you to predict only one thing among a multiple class, right? So we'll have to decide how to use it. But intuitively, for multi-level, you can use sigmoid because you need to predict independently. For multi-class, if you have to choose one amongst all of them, you have to use multi-class, right? So this is something that we can go through. Okay. So now let's go back to our practice labs quickly. So what was our encoding model was? Our encoding model is this, right? Our encoding model has a shape of 784. Sorry, our encoding model has a shape. The shape will be, so the input will be 784. Sorry, yeah, so this is what it is. This is the shape is in 784, right? And I'm saying that reduce from 784, reduce to 32, right? Compression factor of whatever the factor is, so 25% of compression, right? And then decode it. All you do then is basically, you can see this is a way to actually pass data. Okay, and the way you can pass data is via this is directly passing the data. And if you actually pass the data, so model, autoencoder model will look like something this. Pass the model, whatever is your input, pass the full model. Your full model is nothing but, remember, h of x, g of f of x. So this is my f of x encoder, and this is my g of f of x, right? So this is also one more way of writing your code. Okay, randomly chosen, yeah. So if you have to choose randomly, and then if you don't like randomly chosen, what will you have to do? Do we remember? How do we ensure that this 32 is rightly chosen? What will you do to fix this issue of 32 if you don't like 32? You don't even know whether if the images are represented properly, isn't it? So you will have to do hyperparameter tuning using Keras tuner to increase, right? Maybe you will have a range of from 32 to 1024, 5000, you never know. And then you'll run multiple models and find out the best one, right? So that is what it is. But generally you will see that it's in even numbers. 32, 16, 5112, 4096, like that. Okay. And so we'll build our encoder model. This is an encoder model, right? So model goes to this, right? So that's done. So this is my encoded, and this is my encoder. Encoder takes the encoded. Why? When we don't show proper image, then we use this. Okay. When we don't show proper image, then we use this. Preeti, I'm not able to understand. If you can actually explain, it will be great. Okay. So if you see that from an encoder, so we have built our autoencoder model. Okay. Yeah, so I'm not able to. Can you explain one more time? When do we use ReLU? Okay. When do we use ReLU? In the hidden layer? You are saying when do we use ReLU, right? ReLU, right? Okay. When do we use, why, what should we use ReLU for? If you don't use ReLU, what are the other options? It's a question back to all of you. If you don't use ReLU, what should we use? What are the other options that we have? We have sigmoid. You can use sigmoid, right, as an activation function. You can use StanH. But what is the problem with both of them? If you use any of them in the hidden layer, and if your layer is deep, what is the problem with them? Do you remember? I'll wait for an answer from all of you. If you use, yes, you will actually end up having vanishing gradient. And why do we have why will you have why do you have a vanishing gradient problem with TANH or sigmoid? Yeah, problem is right, but I'm asking is why? Because of range, okay, and range is less. Then what happens? Fine, range is less. Then the gradient computation. No, your answer should be, if your range is less, then your backward propagation algorithm will actually compute the gradient, which will also be lesser. and then if two less numbers multiply with each other, it will be more less, right? And it will go to very, 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 very close to, because remember that whole idea of chain rule was that multiplication factors, right? It will multiply, 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 and it will become very, very less. Gradients will go away. If gradients go away, that is a vanishing gradient problem. And if gradients go away, then what will be the problem? What happens to a network if you have a vanishing gradient problem? Yeah, there is no learning, right? Your old weights, remember that function, right? Old new weight equals to old weight minus the learning rate into the gradient, right? That is our general formula, right? So your gradient is none. Learning rate is whatever learning rate you put, it will be multiplied by 0. Your new weight is nothing but your old weight. Learning will stop. No more learning. So hence by default should use ReLU. So whenever you want to explain it, explain in this way. More and more you say, the better for you, because you will go through each aspect of, people will start asking questions. It's also a good way to rehearse. If you are going to go interview and all, it's also, in your mind you can actually reiterate things, right? I hope you are able to understand, Preeti, that this is why we should use ReLU generally and not others, right? And yeah, so at least in the middle layer, you can still use sigmoid on the outside, on the output layer. That's not a problem, right? Okay. So this model maps an input towards, so this is my encoder model, and so that's what I do, right? So this is okay, and then I'll do a compile. Let me load the data. Okay, so this is downloaded the data. So Fashion MNIST is, you can load it like this. It's a good data set. Okay, it's actually a better data set. MNIST was there, but then they have loaded the Fashion. I think it is still 60,000. Okay. Because of this data sets, it's so easy for us to learn. So now basically I will reduce the batch epochs to like 2, and batch size to 140 128. Okay, and so let me go to 20. I think it's not taking so much time, right? So if I do this, so what's happening? The whole of autoencoder model is getting trained, right? So what I'm training whole of autoencoder. Have we seen the summary? We have not, and we started compiling. This is not good. So let's see the autoencoder.summary, right? Always see summary. At least you will have a good idea of what is it. Oops. Okay, it's done. 9 and 10. Okay, done. And you can see this, right? We have one input layer. This is my feature representation. So basically, what you can do is like you can remove if your loss is acceptable. In this case, it is very less, right? We'll crank it up. Okay, we'll crank the epochs, and if its loss is acceptable, you can remove the loss part and take this output, whatever the param is, right? The output shape of it, that for each of them is going to be 32 vector, and this is something that you can go and distribute to others, right? So the output of this, not the model, okay? I'm talking about the output of this particular layer is something will be representational, right? So let's increase it by whatever it was, 50, and maybe it was good at that time, 256. Okay, hope it's not going to take a lot of time. 3 seconds. Okay. Why it is taking? Okay, so let it run. It's okay. It's a very minor improvement. Maybe you have to run like 10,000 times. Okay, and done. Your training is done. Oh, sorry, 50, right? But okay, so it's 100 seconds. So let it run. Okay, we'll see how if it actually reduces. Right now, if you actually do predict, okay, and if you see this thing, this is important, right? This is your original. You can see that this was your original image, and after doing the decoder, you got a shoe which looks like a shoe, but there is loss. This is a lossy compression, and this is what that is what we have to live with it. It's not that bad, but given that this is still a 28 by 28 pixel, but with just one layer, it is not that bad, right? In this case, you can see the checks are gone. This shirt has checks, but checks are gone. This is almost not visible because this image on its own itself is very, this is probably a sandal, right? These two almost look same. This is a sandal, this is a sneaker, but it doesn't look. But others are not that bad. Right? So if you actually project, so this is my X and this is my X pad or X hat, right? And if you change it to, and this is where you can actually use a different loss function, and you can see whether it works or not, right? So we are at the three more epochs. Let it run, and then we can run it and see whether. So that's what it is, and see. And if you actually use matplotlib, okay, it says that use matplotlib. Don't ask. It seems okay. So this is all grainy. Okay, I don't know what has happened. Something must have happened. Okay, everything has come out to be grainy. Okay, so the most of the times what has happened is that you have to restart the model preparation from the very beginning. If I let's do this, okay, and let me train now. Okay, so let me train. So let it run for about 100 seconds, and we can see that whether it improves. So probably what I did is that in between I just did a compile and then I've just changed the epochs and did it right. Sometimes it doesn't work. Okay, so let's see if it works or not. Okay, so do you get the basic idea of autoencoder? There's a lot of usage. So this is variational autoencoder, a slightly model and an interesting take on encoding. Okay, if you take which adds constraints, so this is there's a lot of learning you can do. Okay, from there. Okay, and people have contributed to it. It's not bad to actually go through all these things, and this is all Keras documentation, all open source. Okay, so you can always refer to it, right? Uh, so that's about autoencoding, which is sort of makes us the end of our lesson, which is pretty remarkable, by the way, that we were able to finish it up much before the time, and now we can actually ask questions that you have, okay, that you might have. Okay, let it run a bit. Do you have any questions related to projects? Maybe we can take it now till the break, and then after we come back, we'll open it for much other types of different discussions. Do you have any questions on projects that you want us to know? Did anyone else started the project? I know that you guys have said that some of you will start over the weekend, but I'm just checking if there is any progress that is done. Okay, something wrong in the image. I think maybe you should start looking at what is the problem. So everything is glossy. So what we can do is like retrieve the last layer, okay, of the encoder model. So you can actually start debugging actually what is happening, but and generally it should just work. This is actually a copy of this, right? So this you can see this, right? Just one layer. Yes, let's do that. Yeah, let's do that. I will do that. Okay. So let's go to the self-learning. Right. So which projects are we talking about? Can you please? So I've gone to my assessment page. Which projects are we talking about? We discussed loan. We discussed this house loan analysis a little bit yesterday, right? Which other project? Which project do you want to discuss, or all of it? So this is. Have you started on this? Apart from the node, okay. Both are there are two loans, okay. Apart from this loan, okay. Okay. So lending club, okay. So lending club is what? Okay, lending club. The data is given. Let us load the data. Okay, download data set. Let us load the data. How big is the data? Okay, let's load the data and let's see. Okay, deep learning assisted practice projects. So how big is the data? I hope it's not that big, right? Okay. So let us look at what has been said. What has been said is that create a model that predicts whether or not loan will be default or not. Okay, it is not, earlier was whether the loan will be given or not, but in this case now should a person will default or not. Okay. So basically my target is credit policy, right? One, if the person, no, this is not zero, is the man. Okay, so what is my target? I think this is my target, purpose. Okay, purpose, this is loans purpose, eco credit. So I think this is my credit policy. So perform, okay. So let's do one thing, let's quickly load the data. Without data, it's difficult. So it's a zip file. So what I'll do is like, I'll open the terminal. Uh, where are my 9.3? Okay. So assisted practice, and then this is city projects, right? Okay, so this is my unzip. What is the file name? 158. They are replace. Okay. Okay. So this is let me actually put it in a different folder. This is lending club. Sorry, lending club. Okay. Okay. So let me just put it. Okay. MV155 to lending club. City lending club. So unzip. Okay, so we have the data set, right? So there are three things. We have input.csv, unreadable. Okay, so I'm just gonna, this is your, I think this is someone, okay, I'll just copy paste it for now. Okay, so this is input. Let's open this. This is, let's rename the file. Okay, how do I rename? Okay. Okay. So this is loan data. It's also loan data. Input.csv, output.csv. Yeah, I'm gonna delete your project. Don't worry. Okay. So I just copied it because so that I don't have to do imports. All the imports that you did, right? No, we'll separate it. It's okay. Don't worry. We don't need all those things, right? Always start from fresh. It's always better to start from fresh. Okay. So now that is what it is. So let's do one thing. Let's import this. But we have three files. We have an input.csv and loan.csv. In fact, we can open it, right? Yeah. So this is my input.csv file. Okay. Okay. What is loan data.csv? Okay. What is output.csv? Okay. This is from a competition, I suppose. So we will do. Okay. I think both are same, right? Looks like both are same. Okay. So we will use loan data.csv. Let's use loan data.csv as we have already the feature names on top of it. Okay. So the input.csv does not have the features, but loan data.csv has features. Okay. So now that we have used a starter, okay, we are using Uttam's code to let's load the data. Okay, he has used this. Let's load the data. Okay, and see. Right. So now we have loaded the data. Okay. So credit policy is my target, right? Clearly, right? And okay, it's not that bad. Fair enough. Small, like 10,000 entries. This is good. 10,000 entries. Moderate size, no, only 12 features. I think credit under dot policy is what you have to predict. Perfect. Okay. Okay. Let's go to our assessment lab once and see that what we should do. Okay. Okay. So now that we have loaded the data, what should we do next? Now that we have loaded the data, what should we do next? What do you want to do? Shall we see whether this data is imbalanced or not? Okay. I still have some lot of, okay. Uh-huh. I should have actually deleted and created it. Okay, let me just, oops. Okay. So if you actually do this, so what I'll do is like credit dot policy. Right? So I'm just blatantly using your code. Okay. Thanks for that, boss. So this is what we have. So we can see that. Do you think the data is balanced or imbalanced? So do you think the data will be, so one will be someone who is gonna be who will be repaying the loan, and zero will be someone who has not repaid the loan. So generally, a lot of people actually repay the loan, right? So that is, so till now we are okay, isn't it? So we can see that there is some sort of imbalance. Now let's discuss. Okay, what are the other things that we should discuss? This is a gradable project, so I should not actually do a lot of things. But now that we have data, okay, I think we have a fair bit of understanding on how to handle this, right? Does anyone have any opinion on what should we do next on this? Or are you guys now is that okay? Is this a good enough starter for you guys to start? I mean, Shobha, are you okay? Is that a good enough starter for you to go over it? Or if you have any specific doubts, we can actually answer that as well. Okay, 10,000 data sets, and my target is this. This is still a binary classification problem, 1 or 0, right? These are my features, right? And there is a categorical, so purpose is my categorical. How many categorical? There is only one categorical variable, which is purpose. You can one hot encode it, right? And then you can scale it up, because days with credit line, all these things are very big number. Annual income, installment number, and so on and so forth. You can scale things up and then pass it via neural network. Add as many number of layers as you can. Um, First objective is that if you want me to write, I can help you to write. First objective is build one epoch. Check. It's a binary classification, right? On 10,000, if you this is your class distribution, right? So what is your class distribution looks like? Of whole of 9,000, right? The percentage is 7,000. It's almost 70% plus, right? So even if you close your eyes and dip into the pool, put your hand into this bucket, what is the chance of picking up a specific class? That is your default probability. So your first epoch, the epoch number one, no, that's not, no, yeah, one. Your chance of picking one is how much? Let's say 70%, may not 65%, right? Your chance of picking up one should be 65%. Whatever 7,100, so essentially what will be it? So let's compute it, the value 7,100 plus 1868 divided by sorry, 7,100 plus 1868. How much is this? So this is 80%, right? So now one thing is very clear, you have 80% chance of, by default you have an 80% probability of picking up one, right? Because the class distribution says so. So your first epoch should be good enough. I'm saying just intuitively, okay? Intuitively. So this is a high. This is on favor of one. You can upsample it, but I think Just try it out without upsampling for the first epoch. Upsampling will actually give you an equal distribution, but machine, I think the neural network might learn something, right? That's always a case. So to build the first epoch, check if you are good, then go with it. So what are the tasks that we have to perform? Feature transformation. Transform categorical variable into numerical values. What are the things that we'll use for this? Do we know what we will use for this? We just discussed, right? OHE. Yeah, one-hot encoding. Fair enough. What are the types of exploratory data analysis you will use? Let us make a list of all the exploratory data analysis that you should use. Different factors of data set. It's a small data set. Number of features are okay for you to handle, isn't it? To do what? What is the output of histograms? Have we discussed that? What is the output of histogram? You should have some sort of output. Remember that you should have some sort of output. That is important. Okay? Data is normally distributed or not? Data is not normally distributed, right? We can see the and make some so every time you do a EDA, you must actually infer something. If the data is not normally distributed, then do what? You can check count plot. That's what we did just now, right? We did the count plot on the class variable, right? You can do a pair plot. Please do a pair plot. Shall we do a pair plot? What is our loan data? Yeah, let's do a pair plot. What is the DF? Loan data. How do we do pair plot? Dot. Sorry. Let's look at it. Pair plot. Seaborn dot pair plot. Right. So I can just do SNS dot pair plot. Right. Sorry. SNS. I have to import SNS. Import is there. Have you imported SNS? Perfect. Thank you, boss. This is good stuff. So we can do SNS dot pair plot. Do this. This is small data set, right? So now when it generates, it might take a little time. Okay, when it generates, every EDA should have end with an inference. Okay, please understand that every EDA should have an inference. This is a small data set. So what is inference? That why are you doing this EDA? From this EDA, what did you come to know? From this EDA, what did we come to know? We came to know that there is an 80% bias, or there are more 80% of data are 1. So what is that you imbalanced or not? But then from that, what will you do? Okay, it's imbalanced. You are in a neural network. Well, you can say that okay, this is because of, so I can assume that my average, if I close my eyes and dip my hand, I will get 80% time 1. Then my first epoch should at least be 80%. You do not need a machine learning model if your first epoch is less than 80%. Because it is by default it's given. Think like that. And if you can substantiate it, write it in the code itself, in the code you can actually add markup, right? You can add markup cells and beautify and write and do documentation. That goes a lot. So you can see this. Okay, you can see the pair plot. What do you see from the pair plot? Right? What are the diagonals in the pair plot depict? Okay, do we remember? Machine learning folks, what is the diagonal? Can you find something from your diagonals? Diagonal tells a lot of things, right? Diagonal tells you whether there are clusters or not, right? Diagonals are nothing but univariate analysis, like from this to this. So it looks like there is not much of a cluster at all, right? And there is also, data is well distributed. There is very little collinearity. So you can take some 2 or 3 examples and find out, right? So there's a lot of things that it is saying, right? There is nothing, right? There's like, so I think so basically diagonals define you whether you can actually make clustering properly or not, right? Do you have clusters? Do you have clear clusters? Do you have clear separation on data? Looks like you don't have. right? Or you might be having, but because since the data is not scaled, we don't know. Okay, you can scale. Let's scale it. Shall we scale it? Let's do z-score, right? Import. What is it? Import z-score, right? So you can do this, right? Oops, sorry. And oh, this gives you an array. Acha, acha. So basically before that we have to, so okay. We can't run score because what is the error that we got? Can someone say what is the error? Errors are good. What am I trying to do? Yeah, you can use standard scalar. I just use same thing, right? I just used z-score, but I'm getting a yeah, I'm getting a error. What is the error? Can anyone say what is the error? Why am I getting the error? Because if you remember the data, there is one object, right? Remember we saw that a categorical variable we have to, not typecast. We cannot typecast. What are the things that we'll do before we actually do this? We have to one hot encoding, yes. Unless we would do one hot encoding, it will be a difficult problem. So you can also do pd.get dummies on purpose. Okay, how many? So let's, you can actually find out how many set of purpose and do that and then go do it. Okay, but if you actually, so then you have to do z-score. Okay, if you do z-score, after that if you do z-score, I think it will be good, because that will show you, do you have your diagonals, basically tells you how much clusters you can make, how good is your data distribution. That is nothing but a univariate analysis, right? So and then you can say that, okay, if I do, if I use an unsupervised learning algorithm, I can see clusters can be made. Okay, things like that. Okay, so yeah, beautify, whatever things that we have, right? What are the other thing? Can you do additional feature engineering? You will check, so you can do, right? Now you can also do, so it is building. So you can also do df.core, right? So this loan data.core. This is not right representation. You have to do one hot encoding. After you do one hot encoding, do scaling and then do pair plot, you will see these graphs are getting actuated properly. Okay, so then after you see this, you will see that these graphs, yeah, you can plot heat map. So heat map, as in what heat map are we talking about? I'm talking about correlation, Pearson's correlation, right? So dot CORR, right? So I can compute this, right? Yeah, you can compute a heat map. So this is all of this, except I don't need credit policy. So you can drop, okay, underscore columns, dot drop call, right? Column, and then you have to say this, right? So credit policy. Anyway, let's, you can do this, I'm sure. So if you see correlation regression, you can pass it via heat map, right? And it will tell you that, what will it tell you? Okay, what are the output of a correlation? Again, whenever you do EDA, every time you are doing EDA, there is an output to the EDA. Output means not this output. As a data scientist, you are supposed to verbalize that what you understood from the EDA and mention that, right? So what will you get out from the correlation plot? What are the things that you will get out from correlation plot? Anyone? You will get two things, right? Your objective is to, which features are correlated? Absolutely. If there, we can, yes. If there are features, if we have correlated features, we should not. You just mention that as a part of EDA, that we feel that correlation is there. However, this is neural network. You will not remove any feature. Okay. You mention that since there is neural network and correlation is nothing but a way to represent a linear relationship, right? Yeah, just because, okay, This sentence that you have heard of it or not, sentence is that just because there is correlation, that doesn't define causality. Okay, since we are in neural network world, it is okay if your correlation says that two features are correlated, let the network figure it out and drop it. Okay, so what will network do? It will give a low weightage for those kind of connections, right? Let the network figure it out. So you can say like this, okay, I can see that FICO and interest rate are highly correlated, and if they are correlated, it generally, if you are using a standard machine learning algorithm, we would generally want to drop them, right? But since this is a non-linear neural network based approach, we decide to will continue it and we'll see how it is. You can actually build multiple machine learning algorithms. So what is the other thing that you will know? That what is the other thing? Which features are correlated is one. What is the other one? You can, yeah, you can keep the feature in machine learning also. Why do we drop features? Because they represent the same thing, right? From correlation, this correlation regression, Pearson's correlation is a linear method to find this linkage, right? Non-linearity does not exist. You are in the world of non-linearity, right? So non-linear relationships are, it has linearly said that there is some sort of linear relationship. Okay, that itself tells a lot of things, but let the network figure it out, now. At least in the first epoch. If you are constrained by the fact that there is extremely large number, 130 features in your other example, and of that 122 are correlated, that is that at that time you can use this thing and reduce the feature, right? You now have only 13 features or 12 features. You can actually keep some. But what is the other one that correlation, heat map, or these values will say? We have spoken about correlation among features, and then what is the opposite one of correlation among features? If they are correlated, we should have non-correlation amongst features, but highly correlated amongst features and my target. So you need to find out those features which are highly correlated to credit policy and list them out. Because they basically some sort of linear relationship is there from this feature to credit underscore policy, right? So that is something that you have to do. And do these things in a separate my x and y, separate the x and y and do this thing in your x. Okay? Or something like that. Right? So that is important for you too. So it's very clear, right? You have a negative or positive correlation. In fact, if you see, right, nothing is above 0.53. So this is inquiry last 6 months. Delinquent, so this is 0.53. Everything else is, so this is negatively highly correlated with credit policy. You can take a call like this, that okay, we see that the features are generally representative, but they are not scaled, so we don't know that, right? So scale it, one not encoded, scale it, and then you can come back to this realization. Am I making sense, folks? Are you able to understand what I'm saying, or I'm going too fast? Please let me know. Yeah? Yeah. Think on those lines, and actuate it. Take this as a live project, and verbalize it. Because you are a data scientist, you are supposed to explain, and if you want, you can use t-SNE after you do this thing, or some sort of clustering algorithm to project that, okay, I see some sort of non-linearity. Okay. You can take a call that there is no point in and leave most of the relevant features. You can do these things. You say that no, you up to you, right? After applying modeling, you can straight away go to, so feature engineering. You can generate some. Oh, you're not well, right? Yeah, I also have some sort of cough. It's very cold here. So what is the percentage we should consider for collinearity? Up to you. Put 0.5, 0.6, something like that. 0.6. Anything above 0.7, I think, increase it. It's okay. Right? Depends on data set to data set. 0.5 seems too low. Your object now, basically the question is that do you want to add new features? Right? If you are all from a finance background, try to add a feature. If you not, then little bit of study will not help, will not be a bad idea. Look, there is an if there is an obvious feature which is waiting, missing, right? If it is not, then just go to the model building part, okay? And then in the model building part, go nuts, add 3, 4, 5, 6 layers, okay? However, be be realistic of the fact that you only have 10,000 data set. Out of that, if even if you take 80,000, which means becomes 8,000 data set, right? So then your network, um, have ensure that it is don't add too many layers initially. Start with maybe 2 layers. I think that is more than sufficient. Like for the example, for the MNIST, even with 2 layers itself, we are getting so good results. 2 layers, 784 features. Think about it, right? So this is like 8,000 and validation will be 2,000, right? You don't need so much effort. But again, run first epoch, say that I am good. Then, and don't add any regularization. Then add a regularization, a batch normal dropout, and layer, and then use Atom, or use RMS prop and Atom both. Okay. How to add new features? You have to rebuild. This is from a EDA standpoint, new features. Okay, I don't know. You have to talk to a domain expert. You can talk to a domain expert that can you add a new feature. That's what I said, that you can do a lookup on how things, for this data set, for a lending club kind of a data set, what are the new features that we can do. If you cannot find it, it is okay. It's not a mandatory. But typically what happens, you always look for a good feature if you can find it. And for that matter, we are software data scientists. We might not know about the domain. So you have to talk to a domain expert who can help you in that. Okay. So that exercise, you can try it out for a couple of hours. You find someone, find something good. If not, just move on to your model building. When you go to model building, ensure that you have your validation test, validation set ready, separate it out. In the first model, run the first epoch. Okay. Your architecture is ready. Do not add batch norm or dropout. You add batch norm, but don't add dropout. Batch normalization is, it will be good, right? It will make your output in the hidden layers somewhat Gaussian in nature, right? Which will be good for you. And check whether in your first epoch you are getting something reasonable value. Okay. Once you have done that, add 2 more layers, add 2 more things. Add maybe if you want, you can add a batch or dropout. Okay, just to ensure that from a regulation standpoint. And then you can add both RMS prop or Atom. I'm just saying what is coming to my mind, okay? If you ask me to code, I will code whatever I'm saying. That is what I'm saying. That doesn't mean that it is the only way, okay? So I'm saying whatever is coming to my mind, guys, and there's no script right now, okay? So you can use RMS prop. After this, one thing you must do is do this thing, the hyperparameter tuning. Please do that 100%, because that exercise of coding is very important. Okay, once you do hyperparameter tuning, get the best model, that is what you can project. But one thing is very clear, your model performance should be above 95% or at least 92%, right? I just told you the checklist. Right? I just told you the checklist, right? What we'll do is like we'll come back after the break and we'll make a checklist, okay, of our own. Okay, this is a checklist that you can follow any project for that matter, and it's basically all listing all the things that you already know. It just ensures that we follow it, and if you follow it 4 or 5 times, it will go inside your head and it will be easier for you to execute. I've done so many times now, it just feels natural. But if you feel that I am reading from a script, no. So we can make a checklist. It's our checklist. It's up to you. We can make it anytime. That's not a problem, right? And one thing that you can do. This is a small data set. It's a good thing that you should do is to do some sort of explainability. Okay, find find when in the test case there must be some error that will be happening. Error means your prediction is 0, the real one is 1. Find out why that, where in the layer that bug is happening. Okay, In fact, people who are already experienced on the neural network and they are okay with it, I would, if I have to do it, what I'll do is like I'll quickly finish the model building and focus my work on that thing itself. The integrated gradient I showed you, right? That's a really cool thing that to look at. Okay, so once we come back, we'll keep this discussion flowing. Okay, we'll make a checklist for lending card and we'll publish to all you guys. Then we go to the pet classification and then again we'll publish. And then we can discuss what you want me to discuss. Okay, guys, 15 minutes. Let's come back. Shall we? We are taking a break, right? I'm just reconfirming, or it's just only me that who needs a break. Okay, fair enough. Yeah. Okay. Are we back, folks? Just one second. Okay. Shall we start? Let's start. So we discussed that we said that we will make a list of things, right? For all of us to be on the same page, right? So let's make a list of things. Okay. So what did we said? We said that so this is project. So you can say project plan. Okay. I will actually copy paste and I'll do is like copy and put it in the note. Sorry, the chat window itself, so you guys can all copy it. Okay. So what should we do? So first thing is that we should load the data. Yes, back to learning. So we should load the data and then generally what you should do a value counts on. You guys can also pitch in. Okay. Do a value counts on my class. Okay. All right. So this should give you an understanding of. So in this case, what should you? This should be give you an understanding of what? Let's do EDA, right? And then we'll talk about. Sorry. So this is EDA, right? So this is balanced or imbalanced. Right now, if it is something is imbalanced, then you can take a choice. If imbalanced, what you can do. If imbalanced, then you can try to normalize it, right? So not normalize, upsample it, right? Upsample which one? Or downsample. I think the best is to upsample, don't downsample, right? Which one will you upsample? The class which is less represented, right? You can upsample the class which is less represented, right? You can do it, but not necessarily that you have to do it. If you do it, it's good. You can use something called a smote. Okay, smote can be used. Smote can be used. Okay? It's a good thing. You'll also learn, right? What is the other thing that will give you? So this will also give you. So if you do upsample, or if you do upsample, then your class distribution will change, and whatever the distribution is at the end of it, whether you upsample or not, whatever the distribution. So I'm saying that distribution. I'm saying whatever the value counts is finally should give you an idea of what? Idea of how much should be your epoch 1 on a unregularized and very low, so this is important, very low learning rate NNB. So what you will do is like you make a basic frame basis. So how much it should be give you, right? So basically what you should do, output is that make the network, okay, make your network, okay, run one epoch, okay, run one epoch, okay, one epoch is more than sufficient, okay, ensure that the network is unregularized, okay, ensure that the network is unregularized, which means that deregularized and ensure that your optimizer has a very low learning rate. Okay, you don't want to learn anything. Okay, optimizer has very low learning rate. LR is learning rate. Okay, if you do a fit and then compile and fit, you should get, so whatever is your basic class distribution is normal basics probability should match. What should it match? This is a very common way of doing it, right? Should match the basic class distribution. Okay. So now you can think, right? If you do not handle imbalance, the trick is all in network, and that is the reason I said that do not do it. Okay, because it will be that much tricky to build the network in such a way that it should handle that imbalance, right? You want it to train it very well, because in real cases that is how it will be. It will never be. So don't handle imbalance in the first go itself in real life cases. So this is what it is that you should do. Then what we discussed, do you remember what else we discussed, folks? Need your help here. We've discussed that you can do a pair plot, right? And from pair plot you will see that diagonals, right? So before pair plot, you please ensure that what is the data processing that you have to do from data pre-processing. So this is a neural network. You don't have to do too much data pre-processing, right? In fact, if you go to CNN, what will you do? You can't do anything. There is nothing called as data pre-processing in neural network, at least for images, right? So you just directly give the image. In this case, still it is in tabular data form. You can still do some stuff. So for data pre-processing, what are the things that we discussed? Okay, what did we discuss? Do you remember? So this is one hot encoding of the categorical. Okay, what else? Let's got a categorical variable I'm just putting, and then scaling. Okay, fine. What else? We said that new features if possible from domain, right? That's all we said. These are three things that we said, right? And sometimes if you have extremely large number of features, but if you have large number of features, use dimension reduction technique and then do EDA. So I'm not saying that you use dimension reduction technique and pass to NN. No. You can use TCA, PCA and use TSNE. Na? Okay. Why it's good. PCA is common. Use TSNE. TSNE is important. Okay. TSNE one has to know. You are in the land of non-linearity. Use TSNE. Please. Okay. So this is correct. What else did we do? So yeah, of course, PCA is a linear algorithm, right? Do you remember? Ultimately, it projects all those things and then it actually makes the linear line. It still does the best fit line, right? Of those eigenvectors, right? Library should we use? Okay, let's talk about library also. That's a good question. Okay, which projects we should use libraries? We'll come to the libraries. Okay. Okay. Check for variance. Okay. Check for variance. Do you want to do that? Okay. Check for variance, but variance of, do you want to do that? Or you want your network to speak everything? Okay. From EDA standpoint, from an EDA standpoint, you can project. Your power is neural, the network itself. Okay. Ensure that you put heart and soul in building the network. Okay. if your network can learn the variance and your bias, right? Wow. Then that's the trick that you can. But yes, check variance. As from an EDA standpoint, you can do this, but you want the network to, so there is no output of, you can just observe it. Don't make it biased on the network. So let the network figure it out, right? So now after that we can do pair plot. Pair plot, since this is a small data set for small features set, right? If you do dimensional reduction, yeah, I mean, see, it's a good thing to check. Definitely. Okay. What do you, when you say check variance, what do you mean? Can you explain that? What will you exactly do? Your variance is high, and then okay, for suppose your variance is high. Suppose you have your data or one of the features variance is extremely high. Okay, what are you going to do? Yeah, so but that is wrong, na? Do you really want to drop column? That means you're touching with data, and your this idea that you cannot touch data is not good. You cannot touch data, as in like you cannot drop left-handed data. In real life, that is never the case. Data is preciously observed, right? Preciously got. You got it, right? So that, yeah, so 100% variance means there's a collection. If you have a data collection process itself is faulty. In all of these things, we have assumed that the data collection process is not faulty, right? If your data collection process itself is faulty, then the process itself does not reflect the type of data that you are trying to solve, right? So that in this case, it is already given that your data is clean. Data has some representation of the process that you want to automate. That is important. Of course, from a data scientist point of view, the first thing that you have to ensure is the data representative of the problem that you're trying to solve, right? If it is not there, yeah, I mean, if it is too noisy, yeah, you have to clean the noise, right? But I would suggest that, that is, you can do that, but I would suggest that in this course benefits, focus on the neural network point of view. Move as soon as possible. If you should do it, but can your network figure it out, right? Can your network be so complicated? Can it make that function boundary in such a way that it can actually handle the variance? Because in your real data, you have no control, right? That is your objective, right? So when you do pair plot, what happens? Couple of things happens, right? Diagonals represents what? Do we remember what does diagonals represent? Diagonals, if you diagonals will represent univariate analysis, right? It's every diagonal is basically, yeah. So they will represent clusters, right? So clustering is good if you can find clusters, which indicates what? If you can find clear clusters, suppose in one of the univariate analysis, you will have something like this, right? You might have like this and like this. That means your data is already separable. That particular feature, so this is univariate, for that feature F1, you can have something like this. After this is, please do it after scaling, veiling and everything, right? If you do it, then your data is already very cleanly separable, right? You have done a good job. So this indicates that you have done a good job. But if you have something like this, right? You have muddled the clusters, right? There are lots of peaks and things, then it is very clear. The boundary is not clear. Maybe you might want to do something about it, or maybe you don't want to. That's also fine because your trust is on the is you have to trust on the neural network. Please build a network which can handle everything that you throw it at. That is the objective. Build the network which can handle lots of things, all these things, everything, right? Increase your neurons, decrease your neurons, add more layers. Those are the few things that you can do. If you want, you can create your own custom layer itself. And from this course point of view, focus on the deep learning side of it. So diagonals represents univariate analysis. The rest is nothing but noise, right? We should not say. So rest for the rest, what you should do? Do also pair plot. You should do this, right? And the rest indicates. So these are the signals. Diagonals indicate signals. This will indicate noise, and you can learn something from it, right? So then you should do correlation. core. Again, core is good, but we are in the world of non-linearity. The algorithm itself can handle non-linearity, right? But it will give you some idea. So what we will say? We say that pick. We generally say that pick features. Sorry, identify features. I'm not going to say the identify features which are collinear to each other. You may drop them. I'm just saying that you may drop them. You may drop them, but don't drop features because you think that is. I'm saying that please don't drop it. Don't drop. Not neural network. In any case, in any machine learning, in any problem for that matter, your objective should never to drop data at any instance ever, right? In any case, because the process of acquiring data was hard. It was really tough and it was really time consuming, right? And then dropping anything should be to fit the algorithm. It should be your last resort. So that is what you should always. You should never drop data unless you have a really good solid result. I have not added the handling of NA. Okay, I've assumed that you guys will do it. Do you want me to write? Okay, this is missing value, computation, imputation, all those things. I'm assuming that you will handle that. Okay, impute missing values, right? Or basically NaN handling. Okay, so just remember that this is not finite amount of, so you may drop and then just identify features which are not code, so which are collinear, which are correlated, which are highly correlated only to y, which is whatever you target. But remember one thing, please remember, okay, correlation is not equal to causality, which means that just because they are correlated, that doesn't mean that it impacts the y, and that is more so because of your non-linearity. Okay, you will realize that. Okay, so okay, fine, we have done the correlation. So at least from an EDA standpoint, you are good. What else should we do? Okay, discuss something, right? Sorry. What should we do? This is sorry. I think that's about it, right? So let's do one thing. So let's build what is a model building? Do we need model building? What model will you use? This is a tabular data. Okay. What is your neural network should look like? How many layers to start with? Okay. Layers, number of units. Okay. And so and so. This is not a time series data. This is not an image data. Do you need convolution operation? No. Do you need recurrent? No. So is it dense layer? I think it's more than dense layer, right? So at least from project to project you can decide what you need. You can decide that do we need convolve operation? Okay. Then use CNN. Do we need recurrence? Do we need recurrence, or is this a time series data? Then you know RNN or some flavor. Then use RNN, right? Use CNN, or else for now just use dense layer. Okay? Now once you do this, then how much? So now you have to do basically how many units, and that you can figure it out, right? Start with number of units. Start with a unit of start with some 512 or something. So start with some multiples of 2, and multiples of 2, okay, and then scale it up. So you will have your first model. So but remember one thing, always build the first model. Do this 100%. ensure that run one epoch. After this is over, you should do param tuning, right? Using, what should we use for? What can you use for hyperparameter tuning? This is also part of the library, right? What did we use for hyperparameter tuning, guys? For hyperparameter tuning, what did we use? Keras tuner, yes. What is batch normalization? It's a layer, right, inside. So you can decide, right, whether you want to add just add bench. Then, so do you want to add B batch normalization layer or dropout layer, right? For regularization, right? This we have to figure it out, isn't it? So these are the two things that you can do. This is tabular data structure. So this is Keras tuner norm. Okay, Keras tuner you can use, right? You have to use, not you can. You please use it. Okay. So one of the libraries that you need is Keras tuner. Another library that you need is, what is the mother of all libraries that you need? TensorFlow, right? And then inside TensorFlow, what do you need? Keras, isn't it? So that's about it. Yeah. So hyperparameter tuning is done. Train the final model, and once after you have trained the final model, what do we have to do? Try to do one round of XAI, and you can use that integrated gradient. Okay, just try to see, okay, if you can make something out of it or not. It's good actually. If you really want to go this thing, then you can use also TensorBoard. An integrated gradient is, TensorBoard. TensorBoard is very simple. Tensor. You can see TensorBoard. This is TensorBoard. Okay. So I will just, and you should be able to. It's just one line, not one line. It's like, okay. So where is TensorFlow? Get started. So here in your Jupyter notebook only, you can specify something like this. While you build the model, while the model is building, it can project things to TensorBoard. And TensorBoard, what happens is that it's an UI tool. Okay, you can, and you can create the data, and it just gives you that. Okay, so it's a good thing that you should know. So this is the MLOps part of it. An integrated gradient can integrate, it projects things to TensorBoard. This becomes easier for you to do. So this is a very typical thing that you have to do, right? Have I missed anything? Okay. I think we have a big list of things, right? Did we miss anything? Obvious things that you think that we have missed? Hyperparam tuning. So I would suggest that, so for this benefit, focus on this. Of course, you have to focus on everyone else, but focus on this. If your network can learn all the impurities that data is giving, and you can successfully do that, na? Think about it, right? Maybe you might add to, so one of the things that you are missing is loss function, right? What will be the loss function? Choose the best loss function. Multiples of 2 units. And then what you have to worry about is use your optimizer properly. So I would suggest that start with RMS prop. You can use any of these things, RMS prop or Adam. Adam is generally shown to work really well at high volume. Your data set, some data set is low. The other data set that we spoke about has a lot of data. Okay. Okay. And this is RMS Adam, or what else that should we go? Additional feature engineering to download, you can create TensorFlow backend. If you really want to go one step up, okay, really one step up, then you can actually create a web app. Okay, so TensorFlow web app. Okay, So while where you can separate your inference, the prediction engine separately. So what you can do is like when you build the model, you have built the model and you save the model, serialize the model, and then when you in your inference engine, you can actually load the model and just use some sort of API to do that. This is good because you will also learn a little bit of um, ML ops. Not for this course, but if you have time, you can do it when you are. There's a lot of if you do a TensorFlow web app search, right? Just do this, so you can see this, right? There is a Medium article towards data science article. You can also do TensorFlow serving, yeah. TensorFlow serve, SERVE, okay. So that you can do, or you can also build your own Flask API and various kinds of API which can help you do that. Ultimately, all this thing has to be consumed by someone, isn't it? So that is, I think this is a good enough thing that you can do. What are the other libraries that anyone can think of? TensorFlow, Keras, do you know TensorFlow? Keras, we might need pandas, right? Are we? I'm just writing them. Okay. Pandas, the things from sklearn you need, right? I think sklearn. Let's put sklearn. Pandas, I'm not writing it, right? So and yeah, evaluation. What about evaluation? We forgot about evaluation, right? These are all basic libraries. Yes, absolutely. Nothing outlandish. All basic libraries. So you just focus also on the evaluation, how good your network is, right? Might be this is like, but this is if you go by this, and you can choose to spend most of your time in 7, 8, and 9. Okay, given the fact that you are, I'm if I, if I have to assume, I'm assuming that if you based on where your expertise lie, you can focus on that. But this course was all about 7, 8, and 9, right? While you are actually also go through the data. See, just from a pre-processing standpoint, you can do a little bit of pre-processing. This is still a tabular data, so you have chance to do pre-processing. When we go to the image, what pre-processing will you do? You can't do anything. There is nothing to do basically. Image is there, load it, done. That's it. There is no pre-processing whatsoever. Okay, you can visualize some things, you can categorize something, but that's about it. Okay. Any obvious questions? Do we want to look at the other project as well, like in this detail? Let me just. Friday night. I think Friday night is coming and haunting us. I think this is the right time to start backward propagation. Shall we do backward propagation now? Right? I think it will be good if we do backward propagation now. What do you guys think? No, I'm just kidding. Don't worry. No, no, no. I think this time is needed. This is time for you, okay? The whole course is designed in such a way that last 1.5, like 3 to 4 hours, is all about projects and the doubts that you have, or may have, or you think you have. In a way, it's good that tomorrow is Saturday, Sunday. Think on that and ponder, and we can touch base anything on Monday, whatever, and and redo it. Time permits, right? So let's do one thing. Let us actually, since project is something really important, let's look at the other project. So house loan data analysis. If you look at this particular project, there are 122 columns, right? Or 130 columns. We looked at it yesterday, right? You might have to worry about how do you deal with this 122 columns, right? Um, and think about it, and and stuck and get solve it. So pair plot is something that is out of question. You can't do that at all, right? Calculate sensitivity and matrix. which is sensitivity as matrix. Okay, I'll add it. Yeah. See, this is only possible for, so let me just add 9. So hyperparameter tuning. So now 9 I will add evaluation. Okay. So in under evaluation and metrics, so I'm adding these two things. Okay. So calculate sensitivity. What is sensitivity? In what is the other name of sensitivity? Matrix. Okay. Good point. Do we know? Are we clear what is sensitivity? There's a different name for that, right? Perfect. Very good. So recall. Now the thing is that you can decide what's your precision matrix for confusion. You can also put confusion matrix and decide. So you can decide that is this something that you want to bet on recall, or accuracy, or precision. If it's a healthcare problem, you have to do both recall and precision should be high, isn't it? Or F1 score, either one of that. Right. So you can do that, and when you choose the parameter, please give an explanation why you have chosen. Okay? So that will be good. Now that why part is important because that helps you to rationalize things. In everywhere there is a why. Okay. Why have you chosen recall? Why will you choose F1 score? Right? Why don't you choose accuracy? And so on and so forth. Try to verbalize it and think and verbalize it. It will be good for you. Good. We have added it here. Okay. Okay. Do you want to look for GPU training? So, the first, I assume that for the first one, this housing data analysis, there's a lot of data, right? 300,000 data, right? How much was the data? I think let's look at the data set once, and we will actually fall back to Uttam's code itself. Sorry, Uttam, we are just opening your code. Okay, just trying to understand where how big is the data, so that others are also So if you see this, right, how big is the data? So we are talking about. I don't know what has happened. 19,000. Sorry, I don't know what. Where am I? No, I think I've overwritten. Yeah, just one second. I think I've, by mistake, I've overwritten the whole thing. Okay, this looks like the right file. So now, I think something is not wrong. So I might have so the data is gone. So what I'll do is like, which is fine. No, no. What I wanted to say is that this is 300,000 data set. Okay. Now what you have to do is you have an opportunity to create a true. You have large data, large feature, and for the house loan data analysis, you have the opportunity to create a true machine learning model. Okay, which is beyond, which is some substantial size, right? So what you should do is, so here you have calculate sensitivity as matrix. Why? Because if you reject someone's loan, right, create a model that predicts whether or not will be able to repay or not. It's the same thing. If you say that someone will not be able to repay, okay, you have to say, you have to substantiate it. Now, what I'm saying is that you might require, GPU. And have you guys seen? Let's see quickly how can we do GPU training. Okay, it's not much. I'll just show you. You are okay? GPU training. Yeah. So it's a very simple piece of code. Okay, so this is called as distributed training from TensorFlow, and you can run this in your Google Colab. Okay. All you have to do is like, if you have a GPU, you need to actually have GPU, and you have to add something like this. Okay, you have to have a mirror strategy like this, and then when you do fit, I'll just show you what you have to do when you do fit. Okay, fit. So this is what you have to do. So you have to do with, so same something like this. Define your strategy, and then just put all your model dot things under this scope, and it will detect the GPU and do it on its own. We don't have to do anything. Okay, just search for this distributed training. It might actually give you, it will be good if you can do this. Something to something which is really practical, right? GPU training in TF. Okay, because practically you would need, right? I mean, so this is the TensorFlow distributed training. You can get the whole collab file from there itself. Okay, it basically shows you what to do. Okay, and how to detect a GPU and so on and so forth. All you have to do is just all those things are gone. So all you have to do is, I just see, you can see model.fit, right? I'm just trying to go to the, so this is what you have to do. With mirror scoped this, do this. That's all it is. Everything else is remain same. All we have to do is that we have to give a with scope of this, and it will run in a GPU. And of course, given the fact that you have to choose runtime here, change runtime type, choose not none, accelerator should be GPU. And if you are very feeling adventurous, you can also use TPU. Okay, because that's a large data set, your training epochs might be something that you have to worry about. So now while you do model building, you also have to worry about, what do you have to worry about? Epochs, batch size. What batch size should you use? Just use 128. Okay, to start with. Do a small batch size, so you will see some a faster, sort of learning objective. Okay, choose epochs and choose batch size. Okay, I think we have a good enough list, right? So shall we go to, is there any obvious questions that we want to address on this list? Are you guys okay? Sorry. Are you guys okay with this? Great. Okay. So let's look at the other one, which requires CNN, right? So this is a PET classification model using CNN. Okay, and it builds a CNN model that classifies the give. So what it does is that it gives us CNN. Anyone started this? No, not yet. So build a CNN model. So it's very clear that is already your project itself says that it's a CNN model. Okay. Apart from specify the functional and non-functional requirement, it also serves as input for project scoping. Okay. So this is, you have to use CNN. There is nothing you can do. And in fact, the good thing is that they have given you the layer definitions. Okay, 99% of your work is already done, isn't it? You can provide with a collection of pets, that is cats and dogs. The images are of different size with varied lighting condition. Very good, and that they should use as an inputs. Okay, how big is the data set? Okay, let's download the data set. Yeah. Okay, so it's not that big. Okay, so you have some data, and then ls minus l wc minus, so we have 117, right? Okay, ठीक है. I think this is not bad. 10. Okay. So this is only cats, dogs. Okay. So what is this? This is binary classification or multi-class classification? What will be your last? This is this binary classification, folks? Think about it. How many classes do you have? Two, right? So how many classes do you have? You have two, either dog or cat, right? So what? Okay, let me put it this way. Um, will you use binary cross entropy or categorical cross entropy? Will you use binary cross entropy or categorical cross entropy? There are two separate classes, right? It is not the question whether a dog is there or not. So this is not a binary classification, it's a multi-class classification, right? Your last layer will say that what is the probability of a picture being dog and a probability of picture being cat. Based on that, whatever is the highest probability is something that you will transform into your labels, right? So you have to use a categorical cross entropy. Remember? Understood? If your problem statement was all about do you have a dog or not, so you have only one class. And there you are trying to do two things. So let's be very clear on this is fundamentals, folks. So let us be very clear on that. This is not a binary classification. This is a multi-class classification where you have two class to deal with. And your last layer will have two class. So it is exactly like the way our dummy explainer neural network was. Remember it. Okay. Now the question is that if the input is neither, then what will it do? It should ideally give low probability for both, right? But in this case, you don't have any way to handle that, right? Because there are two classes, right? How many classes are there? How many classes are there? Are two classes, two independent classes, right? What is a binary classification? You have one class. Class is one. But the question is whether the class is there or not. Sometimes the class is there, other time the class is not there, right? So you have one class with two different questions. So that is by, right? So you're that in that way it is right. Like diabetic or not. But does someone has diabetic as well as some other disease? There are two classes, right? Two different classes, right? Think about it. So in your last layer, how many neurons will be there? In this particular problem, how many neurons will be there in your last layer? No, it will not be one, it will be two, right? You need a picture's probability of being dog and the picture's probability of being cat. If the neural network is trained properly, then if you have uploaded a cat's image, the probability of outlast layers for the cat will be higher than that of a good dog. But you will get both the probability. For every picture, there is some probability you will get, right? How much ever low it is, you will get some probability. If the picture is not neither, you will still get some low, very low probability for both. Okay. But only thing is that in this case, it will fall back to something, right? And that's where it is. You will have to put a threshold saying that in the by default threshold is anyway 0.5, right? All these frameworks, when they translate the probability value to the label, they will put a 0.5 threshold, right? Understood? So, but you can actually put your own threshold. You can get the raw probability output from the last layer and put your own threshold. No worries, right? That is what you have to anyway do. So this is exactly like MNIST, but dogs and cat, multi-class classification. MNIST has 9 classes, 10 classes. This is 2 class. Right? So what is the model that we are talking about here? We have an input layer. And see again, this is the run the program for 100, 200 and 300 iterations, right? I think you should be able to run the program for how big is the size is each of them. Oh, so you have train test. Where am I? Also, you have train. Oh my god. Okay. So train test is separate, by the way. So you have cats and dogs. So now are you able to understand what's happening here? So look at the data structure. Okay. Look at the data folder point of view. Okay. You have pets classification. Under that you have data. You have train, and then cats and dogs. So you have to spend a little bit time in making the code in such a way so that all the data are merged together, right? And then put it to the neural network. So that piece of code you have to do. Understood what I said? Before actually putting to the neural network, you have to load the data from various folders. Cats ka cats and dogs is on their own folder. Merge all of them for the train. Okay, so train and test is separate, right? You can see the train, and this is cats and this is dogs. Really cats. Okay. Okay, these are all the cats. There are 10 cats, 20 cats, and you can see there are 20 dogs. Okay, so merge all these 40, and then your final this thing, and they are not. So this is 25 KB, right? So this is not that big, so it is okay. Data is balanced. Good observation. Data is balanced. Perfect. Right. So this is correct. Data is indeed balanced. Okay. Anyway, even if it is not balanced, what will you do? Do you know how to add? Smote will not work for image. I mean, I'm not saying it will not, but it will by default it will not, right? So do you think that you will create new images? You have to do image augmentation. Lots of image augmentation to recreate. That's a different game altogether. Okay. However, now that you know that data is balanced here, and then you have 40 training samples, and which is so then you can run high iterations, right? You don't have to worry about. I was thinking that there will be data is a lot, but data is actually not a lot. Okay, so you can run lots of iterations. We just ran MNIST, so this is 25 KB, right? So I think higher resolution than MNIST, but not too high. How many layers are we talking about here? One layer, 5 by 5 kernel for the first CNN layer. Have a pooling layer. Do we remember pooling of stride 1, stride 2? Okay, stride 2, and then we have a 2 by 2 of pool. Then 32, 64, again 5 by 5, and the dense layer, which is output. So basically 2 layers of CNN with pooling, and then after the pooling do a dropout regularization, add a softmax, right? In this case you have to add softmax 2 classes, define from the training step. Anyway you have to define loss, and then now we just use the right optimizer, and we're done. So I think it's a very straightforward thing. You can use any of the MNIST code that we have and tweak it. Only thing that one has to do is you have to ensure that you read the data from a proper place, right? You put and upload into some NumPy array, right? That is something that you can, focus on, isn't it? Okay, I think we have a good understanding of, really good understanding of the projects now. Okay, thanks for that. I also have a good understanding of the project now. So now let's open it for questions. If you have any questions, I think let us. This is the time for you to and ask. There is also one more. Yes, I saw one more. Right? Sorry, self learning. Yeah. You can take inspiration from this practice project. Okay. This looks like a tabular data. Okay. And the solution is given already. So you can see that, right? Data exploration is there. Feature engineering. Do you have access to this as a practice project where the solution is already given? Can you guys check now quickly? Go to self-learning. You should have below lesson 3, right? Lesson 3 is practice projects. Can I get some confirmation if you can see this thing in your LMS? So if you do see this, okay, just go through the solution, I think, and maybe you can run it. So it has 4 layers, 3 dropouts, 3 batch normalization, and something interesting also. This is that p-ReLU. Okay, there is a version of ReLU called as parametric rectilinear rectified linear unit. Okay, so this is p-ReLU as an activation function. I think it's worth seeing this code. Okay, not much. Only thing is that p-ReLU, there is a p term which is learned by the model itself. Okay, so this is a good exercise. You can see that how it is done. There is also some feature engineering done in the in your so in this solution. So it should give you some help. Okay, great, awesome. Okay, what are the other things that we want to talk about before? We have about 20 odd minutes to go, but I think we should make use of this time to discuss what. What do you want to discuss? Do you want to pick up a topic and we can just keep ourselves ahead of the game? Let me actually just send it. Yeah, PUBG player projects is given, right? Yeah. So I'm sending it, okay? I'm sending whatever we have written. Oh, I think there is a limit. So what I'll do is like, let me send out the, um, just one second, guys. What I'll do is like, I will put it in the community, yeah, community link. That's the right place. I'm just trying to find the community link actually. Okay, this is the link, I guess. Okay. Done. Okay. So what do you say that we should actually pick up from here? Tell me something that we can discuss. Or if you don't have a, see, if you do not have questions for me, then I will pick up something from here and maybe we can start asking questions to you, right? Or the other way around is to have you guys actually taken this knowledge check, right? If you haven't, go and take it, okay? It's like little bit of quiz that is there. It's nice. So tell me what you want to go through. Go through once. Okay. I think this is important for us. Do we understand the last one? Multi-class versus multi-level. Do you want to go through this once? So basically now I think that we should actually do one class versus multi-class versus multi-level. Simulation test. What is simulation test? Oh, acha, acha. In assessment, is it? Let me see. You can take assessment. Yeah, yeah, you can take. Definitely, you can take. So this is a question. Yeah, you please go ahead and take it. So it's just like anyone can take it, right? So I think all of us can take it. This is like 72%. You have couple of hours. You don't need so much time. It should be done fairly quickly. Before that, if you actually come to self-learning, have you actually guys actually watched the self-learning videos? In fact, if you watch the self-learning videos, section 1 I'm talking about, okay? If you go to section 1, okay, watch lesson 6, okay, on autoencoders. And there is also some practice project, okay. It will be similar to what you have seen, but you can look to that. And also look at this, below, so this is the Boltzmann machine, right? RVMs are nothing but Boltzmann machines, which is nothing but a gradient boosting kind of machine. So now, so all of this, yeah, so this, you can use this, yeah. So you can see practice project understanding convolution, right? CNN with MNIST. I think CNN and MNIST, now I think you have almost understood, all of them has CNN with MNIST. But you should actually go through this, chapters as well. It will just help you to boost your understanding. Okay. No, I was actually going through them. It's nice. It's good. Open for question, guys. Anything that you want to discuss, we can discuss. Any? Are we clear now on sigmoid versus softmax? Trick question. This is an interview question, right? And also a practically important question. Which one should we use, right? A lot of confusion is there, but if you understand it, I think it will be great. One class versus multi-class versus multi-level. This is also a very common problem that we see, isn't it? So that is also that one should use it. Anything that you have, guys, I will give you guys 2-3 minutes to ponder upon and discuss. If you want to go through a specific, um, piece of the lesson, I think this is the time. We have about 15 minutes, so we can actually go through that. You know, we can just make use of this time before we take a break, anyways, for the weekend, right? And Monday we will only discuss your question. Remember that, okay? Okay, nothing. Share means, what do you mean by share? Sorry. This is a question. So these are the various topics that we will go through. Oh, no, no, we have not answered. So sigmoid was, so question here is that when should we use sigmoid? When should we use softmax? Okay, okay. So we have discussed it, but for you we can do it one more time. So sigmoid is what? Sigmoid is at the end, sigmoid basically gives you, if you do an output, if you have an input, if you give an input to sigmoid, it will build individual probability for all the inputs. Okay, but softmax will do a running probability for all of them, right? And which means that if suppose you get five, so essentially it's like this. Okay, so you give softmax three numbers, 2, 30, 5, 6, right? So output of this will be probably, right, 0.02, comma 0.9, comma 0. Sorry, 0.1, comma 0.09, right? So this is what the softmax output means. Okay, which means that there is high chance, very 90% chance of being 30. So 30 is translated to 9.9, 2 is translated to 0.01, 6 is translated to 0.09. If you add them up, it will be -1. Sorry, if you add them up, it will be on 1. So that is the softmax probability. So the same thing if you actually pass to sigmoid, right? Sigmoid will give, if you pass the same thing to sigmoid, okay, it might say that 0.3, okay, 0.9, okay, 0.4. So this is an independent probability. This is basically just a number between 0 and 1. You can take them independently. The probability is not across all the samples. So if you have a multi-level classification, which means that your problem statement is to detect multiple classes at one shot per prediction, then basically it is better to, so like if you have a picture, I'm just saying, okay, this is a dog and this is a cat. So you are asked to identify both for the same picture. Till now what we were doing, is it dog or is it cat, right? So in this picture you have been asked that is there a dog and a cat. So there are two levels for this picture, right? You are asked to predict this. So it is better to use sigmoid, because there is a probability of cat also to 0.3 and a probability of dog also is 0.5. That's possible. But if you pass this by a sigmoid, sorry, softmax, what will happen? It will give one of them high probability and other it will diminish. Because all of them, this is individual, this is for across all of this, and this is multi-class. This is what I spoke about. I hope you understood what I meant. Next, if you see softmax equation, there is an E, right, which actually exponentiates that, and then basically adds a probability distribution for all of it, right? So that is the reason. So this is a very clear distinction between when to use softmax and when to use sigma, and only in output layer. Softmax detects multiple class with dependent probability. So this is dependent, right? You add all of them, it will become one. So basically they are basically dependent, right? Sigmoid will create independent probability. These numbers are exactly independent. They don't add up to one. So, and in this picture, in this problem statement, I want, there is a dog, there is a cat, both. So I want both to be detected, not any one of them. So that is a reason you for that, and that is also called as multi-level classification. You are detecting multiple levels, okay, multi-Y. Till now we are only focusing on one Y. So if you have multiple Ys, then you should use sigmoid, because probability of occurring one, probability of occurring cat does not depend on probability of occurring the other class. They are both independent events. Both can happen, not happen. So in such case, you should use sigma. ROC curve, okay. Okay. There is a request to go through ROC curve, okay. ROC curve is, okay, we can, so basically it's area under the curve, right? So you do it like this, right, and then create the triangle, right? So this is what, if the bigger the ROC curve is, the better for you, because your arc is getting better, right? I can go over it, not a problem. From intuition point of view, it's fairly simple. I can go over it. But if you can actually focus on, so ROC curve is good on, yeah, I mean, I'm saying that focus on this part, by the way, huh? From this project standpoint, focus on this part. 7, 8, 9, 10, like this part. It will be good on you, because this is the world of neural network. That is what I'm saying. Okay. So this is ROC curve exactly. What it is. Okay, I think we are getting quiet, which basically sign tells me that you guys don't have anything else to discuss. And wanted to understand. I just wanted to have you checked this recent. So let's go to Hugging Face once, okay? Yesterday we were trying to go. I don't know now. Okay, today is better. So you want to see that, so this YOLO VC is also hosted here. So you see this, right, DALI? Let's do one thing. Have you checked this image generator? Right, so you can say something like this. Um, um, you know, say something which is good. Minion training, okay, neural nets. So what does it do is, basically, given a text, it creates an image, okay? So in this case, the AI is literally drawing the image. Think like that. It is actually creating it, and you can get this kind of models now. These are all called as generative networks, right? Um, I'll show you. Let's see what this guy can do. Okay. So from a model standpoint, there is one more model that has come out, which is actually pretty good and already making a lot of noise. Is this one, right? The Bloom. Where is Bloom? Yeah, so Bloom test. Oh, so it is here, right? Sorry. This is Bloom. So Bloom is a one of the large language model. You can see, right, now that weights and biases, you can see this. It has found something called as minion and is training neural nets. So this apparently is created by the AI system. Okay, this is part of that training samples, which is called as generative deep learning, where the VAI autoencoder that we discussed, right, very briefly, is. This is also part of something called as one type of architecture called as GAN. Okay, okay, so that is important. So if you look at Bloom, right, Bloom is this 176 billion parameter, and you can generate text like anything. Okay, um, so this tool converts irregular words to, and give it whatever, and it will generate the text, and basically it will fill up the things. You should start reading this kind of things, and it will make sense. This has The training data set has 366 billion tokens. Okay, that's a really, really big model. The total training iteration is, you understand this, right? Current checkpoint is 95,000. See now, I just said compute, and it is now, arise, arose, became, freeze, froze, and then it has added something, right? So Hugging Face gives you these models, and which can be reused again and again. This is something that one can reuse. Okay, because I'm sure what they will do is, like, they will release a model which is of lesser, size. This model might be really heavy. It is already pre-trained. You don't have to train it, because it is not possible for us to train. This costs millions of dollars just to train, right? You need lots of GPU and things like that. But you can use the model because they have trained it, and so you can see the use cases. This just came yesterday, day before, I think. But this week itself it came. They've released it this week itself. Okay. The other alternative model that we have is not released. In OpenAI is GPT-2 and GPT-3. You need to actually get access to the API. Okay, and they have actually created the API on top of it. So they are selling it as an API. So I think, and again, we've gone through attention, remember, then to transformer. This is a transformer model. Bloom, big sign, the Bloom is a transformer model. It's a really big model. How big it is, I don't know exactly. As in, like, what is the size, technical specification? We can see this 70 layers, 112 attention heads. The hidden layers are 14,336 of dimension, sequence length of 2048. Yesterday, when we did, remember RNN, or one of the things we did, right, for the sentiment analysis, we have cut it for 500. So for them, it is 2048. Okay, so hardware they use 48 nodes. People who understand this, 8 GPUs of really high bandwidth. CPU memory is 500 GB, 500 and yeah. So it's a really high end. So this was actually given trained on the supercomputer provided by the French government. Okay, so they were training it on the supercomputer itself. Okay, and there is this. Yeah, I was wanted to check that how big is the model, like from a GB standpoint. And I think it's gonna be very big. Okay. So yeah, I think it's about time that you should start reading this and be act on the what's happening with the AI world. It's a very moving field, especially in the land of language and vision. Very very moving field. On a daily basis, there are things are happening. Um, yeah, we'll actually what we'll do is like on Monday. Let us make a conscious effort. So I'm gonna add it, right. Let's make a conscious about to go over links, blogs, good blogs, okay, articles, YouTube video links, okay. Go to this guy and watch this guy's videos. It will blow your mind. Called as Machine Learning Street Talk. Its videos are really long, but the last video was, if you know who's Noam Chomsky, right? He is a very profound figure in AI and language. So he came in the show. But machine learning street talk, Lex Friedman, okay. Lex Friedman, though it's from a philosophical standpoint or from a study standpoint, you should actually go and subscribe to MIT's Open Courseware, right? Stanford Open Courseware. All these things will help you to revise all these concepts again and again and again. Okay. So we will go over the links, blogs, articles, videos, whatnot. It's not a problem. Okay. It will be good on Monday. All I'm asking you is that on Monday to let's be a little proactive and let's ask questions. Let's list all your questions and then come to the session. Then you will have a more output. And again, take an approach that no question is silly question. Everything is open. It's okay. We can reiterate. I really want to start on Monday by doing this small backward propagation thing. Okay. There was a ask for it, and we will start that, and then it's going to becoming open field. Okay. So I think the attention will be big on the starting of the class. Just want to grab that. It will not be more than half an hour maximum. I think it's going to be 20 minutes or so, and then we can open it up for any kind of questioning. Okay. Okay, folks, if there is no other questions, I think we should call it a day. Okay, and have a great weekend. Let's regroup on Monday for our final session and put all these things. So I have already put this thing. So did I put it somewhere, right? Where did I put it? You guys have this text, whatever we have discussing. I think I have put it yesterday, right? So put your comments if you want on the community link, and we can actually regroup there. Okay. Thanks a lot. I guess that's about it for the day. Have a great weekend. We will get in touch with you on Monday. Okay, guys? Thank you. Thanks a lot.